students, we'll go for the next concept of this third semester descriptive problems here. Okay, so we have completed in the last video the 2 marks question. Okay, 2 marks question here. Now we'll go for the next descriptive here. So you can see here in question number 2, so they have asked generally the spin forbidden transitions give sharp peak, explain. Okay, and the marks is 4 marks here. Okay, now here some you have to explain this spin forbidden or sharp. Okay, and you have to explain this. Okay, and since it is in MSc level and what do you say, based on the Orgel and Tanabe-Sugano TS. Okay, so you have to explain in based on this here. So you know that spin forbidden means D5 system. It comes on manganese salts usually. So they are having the D5 system T2G and EG. So like this. Okay, and since any of the transition to takes place here, so what will happen? There should be the reverse of the spin here like this, and that is what it happens to be spin forbidden. Okay, so if you see here it is 3/2 and here it is half plus half 1 here. So it's a spin forbidden here. Okay, so this is a spin forbidden. Okay, as well as since it is DD transition here. Okay, so since it is DD, so same L value, so what happens here? So it is a Laporte forbidden also. This is a Laporte forbidden. Okay, so like this, both are spin forbidden and Laporte forbidden, spin and Laporte forbidden. But the question is why this, though it is forbidden, it is having a sharp. Okay, if you see the Orgel diagram, of this, so it's having the ground state of sextet. Yes. Okay, and if you see when they split, so you will get into the sextet A1G as a ground term, because single it is 6 means only no splitting here. So A resembles the Mulliken symbol of single, this one. So this is what happens here. And if you see the excited state of the same spin multiplicity of in the Orgel, so you can see that this is for high spin. If you see for high spin, so there is no other energy level states here which is having the same spin multiplicity of 6. Okay, there may be 4 spin multiplicity, or there may be doublet or multiplicity, but not 6. That's why there is no transition here for the high spin in Orgel diagram, and you can see there is no peaks at all seen in Orgel diagram. Okay, so for high spin, so there is no chance. Okay, but why the peaks are sharp here? Because this can be explained in TS. So in TS you can see that no doubt the spin is not possible here, but when you go for the high spin here, okay, so this is high spin here, so, and this is a low spin here. Okay, and this is your sextet S here, and this is your sextet A1G. Okay, and when it goes for here at the low spin here, that means your strong ligands. Okay, when you go for here, so you can see that this sextet E can be converted here. So the ground term is going to convert here in the terms of you can see doublet A2G, something like that. Okay, so in doublet form here, so this way it is going to be converted to doublet form here. Okay, and this is what now happens when this is what there is no as such transition here, because whatever the states we are going to get here has no same spin multiplicity, so there will be no transition here. Okay, there will be no transition. But why these manganese are very sharp and very pale yellow? It's because of this. Okay, at strong field what will happen? Doublet is converted, this ground state from sextet is converted to doublet A2G, and you can see that there are a lot of now the excited state which having the doublet here, that is doublet T2 T1G, doublet EG. Okay, doublet T1G, doublet T1G of P, or doublet T2G, like this. Okay, so a lot of doublet excited state will be there, and due to which you can see now there will be excitation, there will be transition in this way, like this. So here, okay, and this of the same energy level will be there here, and that's why not only this 3 4, so a lot of possible transition is possible in this here, in this case here, and that's why it is going to give a very sharp peak here like this, okay, not a broad peak like the other spin allowed complexes. So spin forbidden, this is what the case here, okay. So a lot of weak transitions very is possible here because of the change in the spin multiplicity here when it is in strong ligand field, and that's why the splitting energy level, they have a lot of same energy levels, you can see here, because of the different energy states, and you can see the transition is going to happen here, and because of which you are going to see a sharp state, a sharp, this is going to be seen here, okay. So this is what you have to keep in the you have to explain in this way, okay. The splitting is very much important here because not only this sextet yes here as a ground state, so apart from this you are having the quadruplet G, okay, I will write here sextet yes, so quadruplet G, lot of will be there here, then I have taken only quadruplet G, then quadruplet P, then quadruplet D, then quadruplet F, like this, okay, and they are going to split further, okay. So there G, I think it is going to split in the 4 like this, okay. So 4 it is going to split in this, that is your quadruplet EG, then quadruplet A1G, quadruplet T2G, and quadruplet T1G. So T 3 3 4 5 6 3 3 6 7 8 9, yes, P. Then this quadruplet P is going to split into only one thing, that is your quadruplet T1G. Then this doublet is going to split into two, that is your quadruplet T2G and quadruplet EG. And finally this is going to split into three like this, that is quadruplet F, that is your quadruplet T2G or quadruplet uh, T T2G, T1G, okay, and quadruplet A2G. So 3 3 4 5 6 6 7 3 4 5 SPDF, yes, 3 4 5 6 7 3 3 6 1 7, correct, okay. So this is how they are going to split here, and you can see now there will be, actually there will be no transition here because sextet is there and all these are in quadruplet here like this, but however you can see that this energy, horizontal energy, what is there here, so you can see at the most the in octahedral field, okay, there is splitting in 10 states actually here. So if you see here, all 10 states is going to split up here, okay, and there should be some 10 absorption bands should be observed here, okay, because the width of the peak is directly proportional to the slope of the higher energy state related to the slope of the lower energy state. So that is not so much is necessary here. So what happens here, so you can see here, so horizontal line is having the 0 1, this is 2, this is 3, and this is 4, okay. So 4 transitions like this is possible here, like this horizontal having the same energy like this, okay. So this is how gives a very sharp because of same energy, okay. So horizontal line will be there, so that is what is happening here. So because of this, it is sharp peaks is going to happen because of this horizontal having the energy which is equal to 0 here, so, okay. So that is what that is the reason because of this transition from the ground to the 4 states, that is the reason why the sharp peaks is obtained in this what do you say, in this forbidden bands, okay. So this is what you have to see here. So because not only sextet yes here is a ground term here, so apart from this sextet yes, you can see that the ground state here will be 3 by 2 also, okay. So if you go for pairing 1 2 3 4 5, okay. So this is what having the 5 by 2. If you go for the spin multiplicity, so you can get this, and if one of this is paired now, so you will get 1 2 3 4 5. So 3 unpaired electrons, so you are going to get 3 by 2. If 2 is paired here, 1 2 3 4 5, so you are going to get only one, this is there, so you are going to get 1 by 2. So like this 3 spin multiplicities is been observed for this forbidden D5 system here, and that's why you are going to get not only if I take here S P D E F, okay, S P D F SPDFG I something like that. So I can get here, because of this I can get 6 6 6 6 6 6 6. So these are the different ground terms I'm going to get with the excited state and one ground state. Similarly for 3 by 2, okay, so 3 by 2 I will get as a 4 split 6, and similarly I will same thing it will go, that is your SPDFGHI. Again it 4 4 4 4 4 4 4. So these are the ground terms with having 4 s here with all other things here. Similarly for 1 by 2 I am having doublet 2, again S P D F G H I 2 2 2 2 2 like this. So these are the different ground and excited terms I am going to see for the D5 system, which is having both forbidden as well as spin forbidden as well as Laporte forbidden transitions here. So this is what happens here, okay. And why this sharp peak is going now here, because I said here sextet test in original diagram, no doubt there is no as such excited state having the 6 multiplicity here. That's why in original diagram there is no possible of transitions, 0, okay. That's why it is pale weak color here. But what happens in the Tanabe-Sugo diagram we can explain, because of spin orbit coupling, okay. So because of spin orbit coupling, what will happen, this sextet S, which is having the ground term as sextet A1G or A2G here, is going to be at high strong ligand is going to be converted into doublet A2G. See here, now 2 is there here, see here, doublet. And what you can see here, see here, so there are so many doublet here like this, having the different ground terms, excited terms here, and that is what the possibility of so many excitation transition is possible here. And this is the reason why we are going to get a sharp peak for this forbidden gaps, like this sharp peak, along with some broadness will be there along, but one this is very much important, sharp peak is going to get. And that is what, because of the same energy of the, like as I said here, same energy, this also possibility is there because of same energy. So we are going to get a sharp peak for the forbidden, both forbidden as Laporte forbidden and spin forbidden transitions. So this is what for 4 marks you have to explain, okay students. It's not that something else you put into the answer paper. So there should be a MSA type of explanation with giving some of this diagram of some of the knowledge of the points of the Orgel and TS diagram. So we have to combine these two and answer for this sharp peak for the forbidden gap for this, okay. So not simple it should be. So it should have, no doubt if you answer in 3-4 lines also no problem, but there should be inclusion of what the Orgel and Tanabe-Sugano concepts here. So this is what about the question number 2, and that is your first one, okay. This is what, that is generally the spin forbidden transitions Q sharp peaks explain. So this is how you have to explain based on the Orgel as well as TS diagram here. And the spin allowed spin, though it is forbidden, but what is possibility, how it is going to, according to TS diagram, how it is going to have the same energy 0 transition. There is a lot of energy transitions will be there, and because of that you can see there will be weak but sharp bands here for the forbidden examples, okay. This is what you have to explain. Now if you go for the second question here, you can see here the electronic absorption spectrum of chromium H2O exhibits bands at 17,400 24,500 and 37,500 per centimeter. Draw the Orgel diagram you have to draw and assign the transitions and find out the 10 dq value. See, so this is what he has asked here. So you have to find the 10 dq value. So this is very much simple, and you should know so scoring, what is the marks for that he has asked. Let me see. For second question B question, that is 5 marks, yes. So this is a 5 marks question definitely. So you should draw the diagram of Orgel diagram. So what is that? This one, complex chromium hexaqua plus 3, chromium hexaqua plus 3, chromium plus 3, that is your D3 system. Scandium, titanium, vanadium, chromium 4 2 4 2. So 3 gone means D3 system, yes. 4 2, then D3 system. This is for the D3 system here he has given you. And you have to draw the D3 system here, Orgel diagram. That you hope you will draw that D3 system Orgel diagram. So that I am not going to draw here. So you know that how to draw the Orgel diagram for D3. And the calculation part, what you have to do, so you know that. So it is going to get in this way. like this, and here one more will be there here, like this. Okay, this is how the splitting is going to take place. This is your A2G, okay, and this is your T2G, and this is your T1G. Okay, this is of plus 6 dq. This energy level, you know, this is minus 2 dq, and this is your minus 12 dq. This is what we are going to get for the D3 configuration, which is example for hole inversion. Okay, this example for hole inversion type. Okay, this everything we have learned in the videos. Okay, when we were learning about the orbital diagram, TS diagram, this all things. But how to solve this, the problem here is that what we are showing here, and this is what here, and if you see the orbital diagram so you are seeing there are three transitions here, as in this one they have given. So what may be these three transition, that is what from A to G. So I will write here, so quadruplet A to G to quadruplet T to G, that is your transition he has given is 17,400 per centimeter. Similarly, next one is quadruplet A to G to quadruplet T1G, that is your transition P, or this is F, that is your 24,500 per centimeter, and quadruplet A2G to quadruplet T1GP, that is your 37,500 per centimeter. Okay, so this is how he has given in the paper. Okay, and you have to calculate the 10 dq here. Okay, now this is a splitting energy here, so this is what very much important here, and this is what the transition is taking place here. This is one, okay. Then this is 2, and like this, this is your third, this is your 2, okay, and this is your third transition. Okay, so like this you can see here three transitions you are going to observe here. Now T1G quadruplet T2G quadruplet T1G and T1G F and T1G P. Okay, okay, now you can see here, so always the first transition you have to take here from here to here, that is minus 2 dq to minus 12 dq. Okay, so I will write here minus 2 dq minus 2 dq minus of minus 12 dq. Okay, so this is the first transition here, minus 2 dq to minus of minus 12 dq. Okay, so that is nothing but your itself becomes 10 dq. And what is the first transition here I have given? 17,400. No, nothing to be done here, 17,400. So this will be your first transition. So 10 dq value will be your first transition. 10 dq value directly comes to be your first transition that is your 17,400 per centimeter. This is your answer. Okay, so if you write this 17,400, so you are going to get, along with the diagram of D3 system orbital diagram, so you are going to get the what you say the full marks. Okay, so this is how the you are going to see the what you say the marks here. Okay, so T2G T1GF T1GP, and this is your T1GP, and this is F. Okay, quadruplet, and this is your T2G, this one. Okay, so like this, so three possible transitions is possible here. And if you see the first transition, minus 2 dq to minus of minus 12 dq, that is plus 10 dq. Okay, plus 12 means what happens here, so it becomes 10 dq. So here itself is a 10 dq, that is the first transition is coming. No need to again equate this one, directly you are going to get this first 10 dq only, and he has asked the value of 10 dq only, so nothing else to be done here. So directly the first transition itself is your like this. Okay, so this is your answer for B. Okay, so if you see this D3 system, draw the orbital diagram simple as I have showed in previous videos and or in the class, and this is the calculation part. If you do this, you are going to get 5 marks. This is what. So for this you have to remember this energy. This we have solved in the class. So many problems you have solved. Okay, so this is what. So next we'll go. Distinguish between the following: orbital diagram and Tanabe-Sugano diagram, ferromagnetism and antiferromagnetism. Okay, distinguish between this. Third answer, orbital diagram, Tanagos, ferromagnetic, antiferromagnetic. Very simple, it is C1. Okay, so how many marks is there? C, 6 marks. Oh, it's very major marks here. So very nicely we have to bifurcate here orbital diagram and Tanabe-Sugano diagram. So what points you can show? So very simple, it is original diagram. First point you have to mention is what? It is only for the high spin. Okay, so spin allowed transition only for the high spin. I need not tell this all things, you know this all. So this is TS diagram. It shows only both allowed, spin allowed as well as forbidden, both high spin and low spin, high spin and low spin. Okay, spin allowed and spin forbidden. Okay, so both these, that's what now the question number 1 was, the sharp peak. So that is what a TS you can explain. So that's why both is showing here, but in original diagram it is only for the high spin here. Okay, then second you can write it is more qualitative. This is more qualitative. Okay, we cannot go for the calculation, but this is more quantitative. This one you can quantitative. The second differentiation you can write here, more qualitative and quantitative. Then third, you can take, then we can calculate delta naught value, we can calculate other parameters like Raka parameters, B value, so many things with the TS diagram, but here there is no possibility. So like this 3-4 points you can write for this Tanabe-Sugano diagram, and even diagram also you can explain this Tanabe, this one how we draw this diagram. Okay, in this way, and you can see that this way how we draw the diagram here in this way. So like this one is placed horizontally here, but there is no as such horizontal here, so just we are drawing in this way. Okay, so like this so this is how we can you can differentiate this with the diagram also. So like this you can differentiate this original TS with at least 4 points, 4 to 5 points. Similarly, what is the next here? So he has asked with the ferromagnetism and anti-ferromagnetism, ferro and anti-ferro. Anti-ferro, this also is same bifurcation you can do. So you can write on ferromagnetism, so magnetic here what you can write on here, so that is magnetic moment, so they are going to align here. So ferromagnetic, so they are going to align in one direction like this. Anti-ferromagnetic means one opposite like this. Okay, anti-parallel magnetic moment, so net magnetic moment will be 0 here. So mu s will be always 0 because all get cancels, and this will be high, greater than 1. Okay, so more I can say. So why? Because even if the magnetic moment is even if the magnetic field is removed, they are going to attain for some of the aligned structure here, and that's why you can see here there is been more, and that's why they are going to be attracted to the external magnetic field here. For some example you can give nickel, cobalt, okay, etc., and some alloys you can give the example. So anti-ferromagnetic also same thing here, so 0 net magnetic moment will be there. And for example you can give some oxides of transition metals, oxides of transition metals. Okay, so example manganese oxide, nickel oxide, Mn2, Mn2O3, or MnO2, like this. So many examples you can give for this anti-ferromagnetic. Okay, so nickel is there, so nickel oxides, NiO2, so like this, so many can give. Okay, you can do it. So this is what about the anti-ferromagnetic, ferro and original diagram and TS diagram. Like this here also you can write around 4 points. Okay, with alignment and its magnetic moment value, some examples, and its ferromagnetic properties, anti-ferromagnetic properties, something like this you can elaborate. So it's very simple question, this is, you can do it, but there should be such points should be what I have discussed, that point should be there in your answering. So then only you will get here 6 marks is there. See, so wherever there is diagram is, so here see, that's what I said, diagram is required here. So how this diagram you are drawing for the skeletal diagram for original and skeletal diagram for the TS diagram, and say few 3 to 4 points, very hard hitting points. So that's what here also diagram is required, because 6 marks is there, you have to see the marks. So alignment diagram should be there like this. Okay, and then some points, 3 to 4 points with examples is needed. Okay, so then only you will get 6 marks. So clarity should be there for this question. Even for this problem question, clarity should be there. Problem should be very personally you have to go for the calculation, but not only just writing this, you have to show this diagram also with different energies here, plus original diagram. So correctly, neatly is there, you will get full marks for this also. And sharp peak also, definitely you have to explain where there is TS as well as inclusion of your original diagram. This two is there, and the excited and excited and ground state of the D5 system. So that is there, you will get the sharp peak. So if you explain on this term, you will get the full 5 marks like this, and totally you will cover the, what is that, how much marks is there for question number 2? 15 marks. Okay, so you are going to score for 15 marks. This is how you can plan for your solution. So when you check for the, what you say, your question answers, how you answer. Okay, now we'll go for question number 2. Question is over. Now we'll go for question number 3. Okay, Now what is the question number 3 asked here? 4 it is here itself. Yeah, discuss the mechanism of reaction of the following. Discuss the mechanism of the reaction of the following. So iron hexacyano plus molybdenum octacyano is there, giving you iron hexacyano 3 minus molybdenum octacyano 4 minus. So we have to explain the reactions. Okay, so what is that you are going to see here? So that is very much important now here. Okay, so what is that? Iron hexacyano 3 4 minus plus molybdenum octacyano 3 minus. So here molybdenum is plus 5 8 3 4 5, and here iron is in plus 2 plus 2 state, and this is giving you same thing, iron hexacyano 3 minus plus molybdenum hexacyano octacyano 4 minus, that is your plus 4 here molybdenum, and here it is plus 3 3 3, yeah. So like this, plus 4 plus 3. So he is asking the reaction mechanism here. Okay, so obviously, so you know that it is example of outer sphere mechanism. This is very much important, outer sphere mechanism. Okay, because it is a saturated here, CN8, so this is a inert, and this also hexacyanate is there. So this is what you can see here. So both are having the inert here nature. So when there is both inert is there, then definitely this reaction is standing up with this outer sphere mechanism. This is very much important. Okay, both are fully coordinated saturated complexes. So that is what the outer sphere mechanism. You can see the electron transfer takes place here, and from 4 minus 3 minus it is going to 3 minus and 4 minus. Okay, this is what you are going to see. That is from the plus 2 iron to plus 3 iron, and from plus 5 to plus 4 here. So like this the electron transfer takes place via outer sphere mechanism. This is the first part. You can tell this, and some few parts of the outer sphere mechanism you know that you can choose that also. So that is what they come close together each. Okay, according to that Frank Condon principle. Okay, so you have to write that Frank Condon principle. Okay, so they come close together and they form a precursor of the complex. This is the first point you have to write, and by this what happens here, change in the bond length will be going to happen here. So bond length means what? Compression and expansion possibility will be there here, bond length, because of Frank Condon principle. So bond elongation and compression with the principle of Frank Condon is happening here. Okay, so that you have to write, and there is no breaching between the compounds here. So electron takes place, transfer takes place in the solvent, basis of the solvent here. There is no as such electron like in the inner sphere we are going to observe here. So that is what you can include here, along with some of the points as we have discussed in the regular class here. But this is very much important. 4 points is required in your answering. Okay, very important. Okay, apart from these 3, so T2G EG electrons, so that also you can write. Okay, some 3-4 points which is required, that also you can write. But looking at to these 4 points, we are going to get the marks here. So that is what outer sphere is very much important here. 3, that is your 5 marks is there. Yes. Okay, so presentation and writing, identifying which type of principle is there. This word Frank Condon, then elongation, extra compression, that word should be there. Okay, and precursor, what the precursor is going to form when they come close together. So, and the bridging, whether it is possible here or not. So this is what important points you have to add in this question. Okay, so this is what about the question number 3 A1. Now next you can see here, explain the function of iron in hemoglobin. Explain the function of iron in hemoglobin. Very simple it is. How much marks is there? 5 marks. Oh, so 5 marks. See, explain of iron in hemoglobin. Iron in hemoglobin. See, iron he is asking you. Okay, and you can see that this is for 5 marks. Okay, this is you have to see now, judge, and you can, because iron in hemoglobin, you know that it is heme synthesis, you know, responsible for production of the hemoglobin. This is important. Okay, iron is required for the production of the hemoglobin, which allows for RBC. So this allows the RBC, red blood corpuscles, to carry the oxygen to every part of the body. So every part of the, all part of the body, all part of body. Okay, so it helps for the carrying of the oxygen. This is what, and you see, there is, if there is a what is it, a deficiency of iron, it is going to lead the disease, what I mean, anemia. Anemia. Okay, so that is what, and Iron helps for oxygenation of the blood here. Okay, from lungs to different tissues. So from lungs to all part of the tissues, this iron is helping, okay, for carrying the blood here, okay, oxygen here. So blood pigments. So this is what we have to explain here, and definitely it's having the some part of hemoglobin also you can explain here. So that's what is having the heme and globin here. So okay, so it's having heme and globin part. Okay, so what is heme? Heme is nothing but your non-protein part, non-protein part, heme. Okay, and what is your globin here? Globin is nothing but your protein part. It is your protein part. Okay, so this is how your hemoglobin type, this one iron is been the two is made up of two parts here. Hemoglobin, that is your heme protein, that is your iron here, and globin part, that is your protein part. So that's the structure of the heme here, hemoglobin here. So and that's why iron is very much important here. 65% of the iron is used to transport the oxygen through hemoglobin. So this is very much important. Okay, so hope you understood this, and yeah, and if possible you have to go for what you say, because it is 5 marks, 5 marks means you have to go for the if you want, if you can go for the structure also. Okay, by showing three porphyrin ring. So you, I think you will do it. Okay, so joining this like this. Okay, then here there is your iron, this is your iron, and this is how it joins it here. Okay, and you can make what you say, the what you say, this like this. Okay, somewhat this conjugation you can make, and thing is what that is very much important. So what you are going to add for this, you have to take care for this hemoglobin, because 5 marks is there here. So you have to take care now here. So what this is attached here. So I have given in the what you say, in the regular classes. Okay, Fe+2 state. So here, so iron is in Fe+2 state, oxidation state in the porphyrin. Okay, and and you can see 1358 position CH3 group, you can write it here. So 135 CH3 group. So okay, 1358 position. So there is attachment of CH3. Okay, 1358 CH3, and in 24, so 13124 234 like this. Okay, so somewhat here 24. Okay, so in 24 position you can see there is a attachment of CH double bond CH2. Okay, CH double bond CH2, and 4 then 5, then 6 something here, 6. Okay, sixth, and this is your 7, sixth position and seventh position. So that is the attachment of your propionic acid, that is your CH2 COH, this. Okay, propionic acid. So this, if you attach all this position here for this porphyrin ring here, so you are going to get the hemoglobin structure. Okay, with iron in +2 state here like this. Okay, and this is how it helps for the binding the oxygen here, hemoglobin plus 4 oxygen molecules. So you are going to get here what? So your HbO2 4 times like this. Okay, so this is how it helps for the 4 heme. So 4 heme carries 1 oxygen atom. So okay, 4 heme carries the 1 oxygen here. So this is what. Okay, and that is called your corporate binding also, non-corporate and corporate binding. So what is that corporate binding? Hemoglobin plus oxygen K1, so you get Hb O2. Then similarly HbO2 another reacts with another K2, another oxygen, to give you HbO2 twice. Then HbO2 twice reacts with another oxygen to give you HbO2 thrice. Then HbO2 thrice reacts with another oxygen to give you HbO2 4 times like this. Okay, so like this it goes. This is how it helps for binding the oxygen. So this is called cooperative binding. So once it binds here, so it will facilitate for binding here, then binding here, bind K1, K2, K3, K4. So we have K1 is less than, K2 less than, K3 less than, K4. So K4 is the highest binding. So one will facilitate the another binding like this. Okay, so this is what we can explain, where K1 is very very less than your K4. Okay, so cooperative effect this is called. So this is how we can explain for this 5 marks role of iron in hemoglobin. Okay, so hope you check your answer how you are written. This is major. So if you write in only 2-3 marks, then you are not going to get full 5 marks. If you write in this way of this, you are going to get the 5 marks. This is what about the function of iron in hemoglobin. Okay, so you have to see the marks and explain. 5 marks is there, so definitely all 5 marks. This also is very good. This also is you have to elaborately you have to answer. And last one, determine briefly the Z scheme of the electron transport in PS1 and PS2. Yeah, definitely Z scheme, you know that, very 5 marks question. So we have solved this in the class also. So PS1, PS2, is it right? So 680, 630, you can see here PS2. So it is around 680 nanometer. 680 nanometer. You can see the electron is excited here with when it is been sunlight is been fallen on this pigment here. Okay, so there is some manganese here, so water molecule will be there. So water molecule is going to liberate the electron plus proton here. Okay, and this electron is excited here now here. Okay, in the upper case here, and to this there will be some manganese acting as a catalyst here. And there are so many now. What happens, electron acceptors, I can say. So here electron acceptors will be there, electron transport system will be there. And here it is going to go for what here light harvesting pigments, you can say here. And here it will go to PS1 now here. Okay, so here also PS1, what will happen here? So here also excitation will takes place here, and here also there will be jump of the electron here. Okay, and further what will happen here, there are some electron acceptor here, so it will come down here. Okay, and finally you can see here, so NADP plus is converted to NADPH2. Okay, so here that is a reduction here like this, and the proton here, that swing will be there like this. That also you can explain here. So here you can see that the ADP is converted to ADP is converted to ATP. Okay, so this also you can explain here. And most of the electron acceptors you can name here. So I have written here electron acceptors like this, all the things. So you can name some like cytochromes electron acceptors. Okay, like cytochromes B6 we have learned. Okay, so that you can write it, some of the electron acceptors here. Okay, then PS1 chlorophyll center, you can write chlorophyll A. Okay, red light 700 nanometer. So this thing you can explain here. Okay, so light and this is your dark reaction, and this is your light reaction. So PS1, PS2, and here where there is reduction here. Okay, so reduction, and where this is a formation of your CHO carbohydrate, so that is your dark reaction. So here this way you can explain. That's why here Z scheme. So properly these all things should be included here. Okay, 680 nanometer, 700, 680 nanometer, 700 nanometer, and these all electron acceptors. I have named only one cytochromes. So if you remember, if you can give here 2 more things here. Okay, and this is important here finally. Okay, and here ADP is converted to ATP. So this also you have to mention here. Okay, and some points you can mention. Okay. So the electrons not used as they pass through the electron chain here to PS1. Okay, like this. PS1. So whatever excited will be there, that is going to be converted coming to the PS1. So there also will be a chlorophyll reaction center will be there here, PS1. Okay, and it is going to absorb the 700 nanometer here at the PS1 here, and that has been excited here. So and transfer to the electron acceptors here, same thing. Okay, again the molecules redox potential, high potential, and it will come down. And here these electrons, then they are moved downhill here, and to the molecule where it is energy rich in NADP here. Okay, NADP, and okay, and this in this NAD reduces this NADP to NADPH plus H plus. Okay, this whole scheme of transition of electrons from PS2 to PS1. So PS2 to PS2 to PS1 here. Okay, and right from reducing this NADP plus to NADPH plus. Okay, so this is your the whole Z scheme, you can say. So where this is a light reaction, and this will be your dark reaction. So like this you have to explain this for this question. Okay, Z scheme. Okay, so 5 marks is there. So examples and some so what I explained now, so that points and everything should be covered here. So that I hope if you write that much, definitely you can think of getting at least 4 to 5 marks here, full marks. Okay, yes. So now I think we are going for the next question number 4. Already it is half an hour video now. so because of time in this one, so I will solve this for rest of the question now in the next video. Okay, so I think you can guess it for now. Two subsections here, question number 2 and question number 3. 15 plus 15, that is 30 marks questions we have solved today. Okay, so just check it. Jet scheme already we have done in class, so you can see it, but what points I told you now, diagram plus what you are going to add there, so that is here also everything we have discussed. Okay, so hope this video will be helpful to you. So rest of the questions here, question number 4, I think from 4 we have to start. 4, 5, 6, 7 is there, so probably we will complete this in the next video. Thank you.